was very careful there to lead the applause with the AV crew. It's a very silly presenter that doesn't get ahead of the curve when it comes to thanking the people in charge of the microphone. They do a thankless job, and this is not necessarily a space designed for high-tech presentations. Anyway, I'm not really here to talk about microservices at all, which is a nice departure for me because I get sick and tired talking about them. But I am going to be talking about words and meaning and how we often use words in ways where we think we know what they mean, but it turns out that other people have a very different view. I spend a lot of my time talking about architecture, and architecture fundamentally we can think of in terms of boxes and, of course, the really important things being the arrows between them. We often joke that this is what architecture is. Sometimes I get involved in more interesting conversations like what's actually happening inside the boxes? Or how big should the boxes be? Or maybe, how small should the boxes be? Should we actually have fewer boxes and maybe take the boxes that we have and break those up into smaller boxes? Probably we should. Of course, there's really important conversations to be had, which is not necessarily about the size or what's in the box, but more about what shape the box should be. And I have clearly made my own personal stance because I am part of Team Hexagon, Go Team Hexagon, right? But today we're not going to talk about the boxes at all. We're going to be talking about the arrows. I did a whole masterclass on Monday all about the arrows. The arrows between our services. And so when I do talk about microservice architecture, I talk about these hexagons and these boxes and the interactions between them. When I draw an arrow like this, what I'm referring to is a logical dependency. I am showing that this service on the left-hand side depends on this other service on the right-hand side. And then the conversation becomes, how do we implement those arrows? How do we take this logical interaction and convert it into something that we can implement? And there are lots of different styles of communication. So in this example here, we're showing that return service depends on something the shipping service wants to do. And this talk is fundamentally about the distinction between these interactions in terms of synchronous versus asynchronous behavior. And I have struggled with this distinction for a while. In general, I instead prefer to start the conversation around the two main styles of communication that I see and I've tried for years just to sidestep this discussion because it is a problematic division. So instead, I talk a lot more about the stylistic differences between interactions, between this idea of request response and event-driven. And so when working with teams who say, oh, should I use Kafka or GraphQL? And it's like, well, those are two incredibly different things. Maybe we start the conversation here with this particular interaction you want to create. Which one of these two camps is closer to what you're looking for? And that in turn will help shrink your solution space. We think of request response as being one of the most commonly used interaction models. It's common, it's familiar. One service is making a request of another service. I am asking for something, I want some help. I want you to do something like this. This is not narrowly fetching data. This is how one service requests functionality from another. And we really hope, we get a response, right? That's what we need. We need the response. And actually, I found the distinction between this way of working and the event-driven world to be one of the most fundamental because it shifts so much of how we think about how we build our systems with all kinds of benefits and also costs. So with event-driven interaction, we get to a more both passive and also reactive model. In this situation here, an event has been fired, broadcast. We think of an event like a fact. Something has occurred. We've just received 10,000 copies of David Hasselhoff's greatest hits in the warehouse. And it is vital that we let the world know. We have Hoff, so much Hoff. And with an event-driven system, you create these lovely interactions where different services are able to react to that same event in the way that suits them. In this example here, we might have a promotion service that uses the stock level notification as a way of automatically discounting a product. The wishlist service might though let people know that the Hoff's on its way, you ordered it, it's coming. Two different services, they're not being told what to do, they know what to do. They know how to react. Event-driven systems are often much more loosely coupled, have an even distribution of smarts, but will also fail in ways that are utterly bewildering and have a higher degree of complexity. It tends to be my happy place. I find this distinction easy to talk about. They are quite different. They're quite different. But unfortunately, lots of people really want to talk about this. And so I tried talking about it for a bit, couldn't find the right words, tried a few more times. In the most recent edition of my book, I tried again to define what these terms mean and realized that I'm still not happy with them. So I sort of think, well, I had to take another stab at all of this. And I was encouraged to write this talk because of this blog post, Substack post by Pat Helland. Pat Helland is a pioneer of computing. This is a very good signal-to-noise ratio Substack. And in this post, he is making the argument that we should rename eventual consistency. Because he says that we use the term eventual consistency often in very close proximity to discussions around consistency in the area of things like database transactions. But the word consistency in a database transaction has absolutely nothing whatsoever to do with eventual consistency. Nothing. But the words are the same, and so it's confusing. Pat is very smart, and therefore he's come up with a better term for this, eventual convergence. The replicas will eventually converge once they've processed all the messages. It says he's a smart person. I thought maybe I can be a smart person when I grow up. So I thought I'm going to take a run at this and try and get to the bottom of what asynchronous means to people, and maybe I can come up with some better terms. Spoilers, I failed. However, the journey is fun. But coming out of this journey, what I've discovered is that there is no consistent definition of what asynchronous communication means. None at all. So we should probably stop using the word. Now, obviously, because I've got a crack team of researchers, that before the enshittening of Twitter, I used to use Twitter as my hive mind. I put out this request. I said, hello, everybody. What do you think the term asynchronous means to you when you're thinking about communication between things? And I read the books and I've read the papers, and we'll come to some of that in a moment, but I wanted to understand what people out there thought this term meant. And what I found was quite interesting. So, shocking is maybe not the right word, but I want a bit of hyperbole. I had to just follow a talk about robots. I mean, come on, right? Anyway, here's from the first response I got. It's from an old colleague of mine, Darren Hobbs. And so Darren said, well, for him, asynchronous communication is about the difference between sending an email and having a phone call. And there's something about this that feels like it makes sense. I pick up the phone, I ask you something, you give me a response, we're having a conversation. We often refer to that in terms of team dynamics and communication as a synchronous form of communication versus asynchronous forms of communication between people via an email. I send you the email and at some point you pick that email up. There's something interesting there about that distinction. So there's something there that was kind of interesting. However, it does sort of imply a speed or a latency element. If I need a quick answer, a phone call is a quicker way to get that answer. But email might take longer. However, some of the lowest latency systems I've worked on have been fundamentally asynchronous in nature. So in the context of computer-based systems, that idea of time doesn't necessarily feel right. But there might be something to that. So I was sort of thinking, okay, well, that's interesting. Well, what else have we got? So while this Twitter thread was going on, I thought I'd go and take a look at the Reactive Manifesto. So hands up if you've read the Reactive Manifesto. Keep your hands up if you understand the Reactive Manifesto. All right. So I'm going to poke fun at the Reactive Manifesto. I don't like punching down, but the people who wrote this are smarter than me, so it feels like I'm punching up, and therefore it's okay. There's a lot of hard work went into writing this document, and the second edition was significantly better than the first one, but it is flawed, and we'll talk about why. But these very smart people have made an attempt to define asynchronous communication. So while my Twitter thread was going on, I thought I'm going to dive deeper again into this and try and tease apart what these people think asynchronous and synchronous means. And they've taken an effort to define these terms. So here we go, here's their definition. It starts well. The Oxford Dictionary defines asynchronous as not existing or occurring at the same time. We'll come back to exactly what the Oxford Dictionary thinks a little bit later on. In the context of this manifesto, we mean that the processing of a request occurs at an arbitrary point in time, sometime after it has been transmitted from client to server. Okay, let's take another look at this. The processing of a request occurs at an arbitrary time, sometimes after it has been sent. So with asynchronous communication, I process something after it's been sent. What? You mean as opposed to processing the request before it was sent? Like some kind of Doctor Who-based networking protocol where packets would arrive before they were even transmitted in the first place. So this is completely meaningless because it doesn't mean anything because all communication and interactions work in this way. So this is not a helpful statement. But there are other bits in the document which I think are much more healthy and much more useful for us. So here's one. So they go on and say this is the opposite of synchronous processing, which implies the client only resumes its own execution once the service has processed the request. This is more useful, and we are getting closer to something. While this is going on, the thread is still going. Here's Steve Smith, who's a friend, focuses a lot in the area of continuous delivery, nice man. He said for them, asynchronous means TCP, the connection is open for the duration of a communication. I said, does that mean if I'm not using TCP, I'm not asynchronous? And he actually clarified. He said, what I actually mean is, I assume with asynchronous communication, you're not blocking for a response. That is precise. That is explicit. That is actually what the Reactive Manifesto is referring to when it talks about the client isn't waiting. So they're talking about non-blocking. Here's the thing. The concept of non-blocking is a precise and explicit concept. It's a much more useful concept than talking about asynchronicity. So let's take a quick look at what non-blocking is about, because it is useful, but also limited in its use. Let's take a simple scenario here. We've got a service that's going to handle enrollment. So maybe this is like a little simple orchestrated process. There's a few things that we need to make happen as part of this process. When I'm enrolling a person, what I'm going to be doing is awarding them some points. So I send a call to the loyalty service and say, hello, please can I have some points? I also need to go to the subscription service and upgrade the subscription. From a logical coordination point of view, these don't have to happen sequentially. Right? There's no implied ordering needed here. However, if we think about a naive implementation, we could imagine a piece of code that looks a little bit like this. The first line of code here, this assumes I'm using some kind of RPC-style abstraction. I'm calling award points on the loyalty service. So that line of code is going to execute. And so when I execute that line of code, let's imagine I'm using gRPC under the hood. I'm going to open a HTTP connection. I'm going to send some bits and bytes. It's going to reach the other server. The server's going to take that information I've sent it, hopefully handle that and send back a response. And once that response comes back, that line of code is finished executing, and the next line of code executes in my client. Right? So the award points call happens. It completes. I get the response. I can then now go on and execute the next call. So this is sort of fairly straightforward, understood, right? So it's only once we've completed the call to loyalty that we can make the call to subscription. This is what we would refer to as a blocking piece of code. We are blocking client execution based on the results of a server completing some kind of response. And blocking calls are not great. And the reason for this is often related to latency. In this situation, the latency of this operation is now going to be bound to be the sum of both of these calls. So let's say, for sake of argument, the first call took 50 milliseconds, the second call took 150 milliseconds. That means the total latency for this operation is going to be at least 200 milliseconds in total. And as we increasingly distribute our processing logic, latency often ends up being the enemy. The longer things take, beyond the fact our users might get frustrated, the longer we're holding on to computing resources, which increases contention, which makes these systems harder to scale. Being fast is normally better than being slow. And of course, this gets even more problematic when we consider that latency is going to vary. You look at, so if you would have looked at the histograms of, say, latency of services. If you've got multiple calls chained together, what you'll tend to find is your latency distribution will increase even more. You're more likely going to see things like tail latencies as well. So an obvious improvement here is to do both of those calls in parallel. Find a way to not block while we make the other call happen. And this is actually something which in this day and age is very, very easy to achieve using something like a reactive extension. So these exist for all the major programming languages, but we're basically making use of things like promises and futures. Because what we'd like to do is, rather than doing this and then this, instead, we'd just like to do them both at the same time, but do so in a way which is easy for us to write and reason about from a piece of code point of view. So this is an example of some simple syntactic sugar that we might use to make this happen. So in this example, we have wrapped the execution of these things in what's known as a future. Exactly how this will be done will vary on the different implementations that you might have. So a future is a read-only type, and it's a bit like Schrodinger's cat, right? You know, that at some point in the future will have the value you want. Hopefully not a dead cat. So in this situation here, the way things work is when I execute that first line of code and my client code goes to the next line, I haven't actually necessarily made the service call yet. What's actually happening is everything inside that parentheses are being packaged up into a thread, probably, and behind the scenes, that call is being executed. So when I start executing that next line of code, it's possible that the first service call is already happening. It may not yet have been scheduled, but it's going to happen somewhere in the background. I'm no longer blocking execution. And so if this happens perfectly, we would imagine now that we can significantly reduce the overall latency of this operation, because these calls should now be happening fairly close together. And so if we imagine that before it was around 200 millis, we'd now be looking at around 150 milliseconds because we've managed to do these two calls in parallel. This is good stuff. This is non-blocking. Now, of course, everyone says, oh, it's got to be non-blocking. You can't block. Got to be non-blocking, non-blocking, non-blocking. Non-blocking is going to solve all your problems. And then I'm like, yeah, but we sometimes need responses, right? We might need answers. That's often the point of request-response-based communication. Maybe I want a piece of information back. Maybe I just want to know, did it work? Something simple. So non-blocking code is great, but you need the response. So in this situation here, once I've got to this point, those two calls may still be happening. They haven't yet completed. But I might need to know the answer from the award points call. Did the subscription upgrading work? So how do I solve that? Well, we need to wait, don't we? And so I might do something like call await. So this would block and wait until the values of these futures has been computed. And now we're blocking, right? Which is not to say that the concept of non-blocking code is meaningless. It's still a good idea, but you might need the answers, right? And the logic of your processing might require you to wait, because until you know something worked, you don't know whether or not you should do the next thing or the next thing. Causality, turns out, is often important. So even non-blocking calls can end up blocking. However, if you can make use of non-blocking calls, in general, it's a good idea. You'll find that you will decrease latency, and the syntactic sugar we have around the reactive extensions has only got better in most programming languages. And so in general, you'll end up with more efficient code if you can embrace the concept of non-blocking. The thread's still going at this point, right? So let's come back to our thread. Here's Graham. The definition I've been using is the sending service doesn't wait for completion of the receiving service before continuing and or completing its own work. So Graham, again, is talking here about the concept of non-blocking. Graham was one of the architects at Tyro in Australia, which is a sort of payments company and a bank. But now I think about it, I think I also expect temporal decoupling Again, that sounds like some Doctor Who stuff, doesn't it? I also expect a temporal decoupling from the receiving service's availability. There was a number of other people that said similar things. So here's Benjamin Johnson. Sync communication, there's direct communication, whatever that means when you look at how networks actually work, between the sender and the receiver. Async, there's an intermediary involved between the sender and the receiver, for example, the message broker. Let's talk a little bit about this idea then of an intermediary. This comes up a lot. Asynchronous to a lot of people means you've got a broker. And this is the most common intermediary we might see. So let's talk about why we might use it and what this temporal decoupling means. So I've got something I want to send from A to B. I generically say if I'm using a message broker, I'm sending a message. A message could contain a request, or could contain a response. It could contain an event, whatever. So rather than sending it direct to service B, instead I'm going to give it to the broker, and the broker is going to deliver that message once the recipient is available. So initially, perhaps B is already got other work it's doing, so it can't take on board any more work. Maybe it's offline. But when it becomes available, the broker will deliver it. So this is what we call temporal decoupling. If we have two services which are temporally coupled, in the context of inter-process communication, what we mean is that I need to be able to talk to you at that same moment in time for this operation to complete. We are coupled in time. With a broker, I get to temporally decouple things. And that means I can still try and get things moving even if you're not available. We also use temporal decoupling in different contexts as well, but this is how we use temporal decoupling in the context of inter-process communication. This is the main reason people use message brokers. It gives you some improved robustness, and it gives you this property of kind of guaranteed delivery, whatever that means, and we're getting the broker to do that for us. Useful things, kinda, right? And we have this other nice imagery coming. This person said, asynchronous is like dropping snail mail in a red post box and getting on with your life, and then bam! One day, Postman Pat stuffs something into your house mailbox along with millions of coupons and charity mailers. I'm aware that Postman Pat might be a UK phenomenon, so this is Postman Pat. This is the OG Postman Pat. The new one apparently is all computer generated, has a hovercraft. This is Postman Pat and his black and white cat. But we have this idea of that metaphor of the message broker as a mailbox. These are American mailboxes. In the UK, we have letterboxes because we won't automatically shoot people when they come onto our property, right? But here, you pop things in the mailbox. You might be away, you might be at work. You come back from work, the letters are waiting for you. The mail system and our mailboxes has temporally decoupled us from needing to be at home when our post is delivered. It is a useful concept. And there are different variations on how we can implement this inbox pattern. Brokers are an obvious way of doing it. You see people doing it with databases, and that can work quite well. You can do this with file systems. A huge amount of inter-process communication historically has been files. One program puts a file there, and a different program at some point later on picks it up. Most mainframes work in this way. You could use email for this, for implementing inter-process communication between services. But don't, because it's daft. It's theoretically possible. The key thing here is the sender of the message doesn't need to worry about whether or not the recipient is currently available. They might care whether or not it is available later on, but at the moment of sending, I don't need to worry about it. This is really useful. It's freeing. It's mentally freeing. However, for that to happen, we need to have trust in the intermediary. This is why we need our brokers to be good brokers. So in this situation here, I'm sending a request from A to B. I put that request onto a request queue. The request queue then, when B is available, delivers that request to B. B does the processing, and I send the response back. This is a classic example of request response over queues, and it's absolutely fine and dandy, and it's great. But oh no, we start introducing new problems. You see, when we deploy services, we typically have multiple instances of a service. In this example here, I have two instances of service A. The first instance of service A sends the request. The response gets processed. It comes back on the queue. And theoretically, any instance of service A could pick that response up. Some people see this as a problem. I see this as a benefit. Stateless processing is what we're aiming for here. What you want is all the context of the message is all we need to be able to process that message. Whereas if you're doing stateful processing, where you're basically keeping memory in state, you need that response to come back to the same thing that sent the request. And the problem with that, of course, is, well, what happens if your machine, with all that stateful processing in it, falls over and crashes? You then lost all that state. And you say, don't worry, I've got some really smart, complicated technology that I'm going to have to pay a vendor for to do magic replication of data between my nodes. And it's like, why are you making your life difficult? Just do stateless processing. And actually using things like message brokers for request response-based communication tends to force you down that path of stateless processing. Coming back to this example, we do have this issue about what happens if the process dies partway through, right? In this example, because we are probably opening a network connection from one server to another server, I'm sending you stuff. By definition, the responses are going to come back to the same computer. However, now if that client dies partway through this processing, we have a problem. What do we need to do in that situation? Typically, the answer is, well, we'll just restart the whole process. And if it's not overly a complicated process, and if your operations are idempotent, that's absolutely fine. But it's arguable. But I think that using intermediaries with things, especially for things like request-response-based communication, but even for event-based as well, it tends to guide us and force us towards stateless processing, which is always preferable. If you're somebody who thinks you might want to do stateful processing, you're probably wrong. But even if you are wrong, I hope you're having a good time and you've got some PhDs knocking around. So we've got all these competing definitions. We've got a definition around immediacy. Is it fast? Is it slow? I don't think that has any meaning because that's a bit of a different thing. There's the temporal coupling problem. There's non-blocking calls. There's the concept of, intermediaries as well, the brokers, the databases. So which one of these is asynchronous? Are they all asynchronous? Is some of them asynchronous? But some people only think some of these things are asynchronous. Does it matter? Words have different meanings. Now, I'm aware not all of you will speak English as a first language. I barely do myself. But maybe a quick quiz. Does anybody know which word in the English language has the most meanings in the dictionary? Go ahead. Set. I love the fact that set has the most meanings in the current full edition of the Oxford English Dictionary, and get is also like a close number 2, which for me as a computer programmer feels quite nice, right? They're quite close together. So set in the current full edition has the most meanings. In the next full edition of the dictionary, which is coming out in 2035 or 2037, it's going to be run. To put this in context about how many word definitions they have, set has 430 meanings. Run currently has around 645 meanings. Do you think you know all of these? No. It doesn't matter, does it? It doesn't really matter. We're used to words having different meanings. So how do we just work out what these words mean? When someone uses the word run, how do we know what meaning of run they're thinking of? Well, we derive meaning from the context in which the word is used, and one of the ways we enrich that context is putting other words around it. I had a great conversation with Ian Cooper. Often people have a hinterland, right? There's things they do outside of work. Ian Cooper's hinterland is like the Alps, right? Because of course he studied semiotics at university. So he was explaining to me, well, about the nature of meaning. The meaning of a word becomes more narrow as we add other words around it. So let's try an experiment. Let's pick run. I want each of you to imagine right now what run means to you. The first definition of what run means to you. I want you to have that in your head. And I'm going to put some words around it, and let's see if we're talking about the same thing. The issue got worse the moment the program was run. Maybe some of you were thinking about exercising. I mean, it's unlikely in a tech conference, but maybe some of you are thinking about exercising. Let's try it again. Think of a different definition of the word run that you might have. The economy crashed due to a run on the banks. Now, it's possible that I used the same meaning that you had in your head, but we couldn't confirm that until I put some more words around it so that we now can be on the same page. And so when we communicate, we are doing this all the time. We are putting extra words around other words, and from that wider context, we are hopefully on the same page and able to communicate. Context is important. Coming back to context, the Reactive Manifesto, with their definition of asynchronous, the Oxford Dictionary defines asynchronous as not existing or occurring at the same time. This, by the way, is what you get if you go to Google and say, what does asynchronous mean? This is the first definition that comes back every time. You go to the Oxford English Dictionary. If you're in the UK, you can get this is freely available to you, the full copy, if you've got a library card. And so we can look through all the definitions. And it is, in fact, look, it's the top one, number one. Context. I mentioned context being important. And the Oxford English Dictionary gives us context. It explains where these words come from and the context in which they were first used. And we look and we see, oh, look, originally this was only used in medical contexts. And this is a word that was kind of from the 1800s. No, even earlier than that. So I thought, well, hang on a minute. Maybe the Oxford English Dictionary has come to my rescue after all this time. Maybe they've got a definition for asynchronous in the context of computing. And they do. They have more than one, in fact. The one that's closest to communication between services is this one down here. This one as well is kind of confusing. This is all about clock signals and things. This is more about internal asynchronicity. The one down below is more interesting. Designated data transmissions in which packets of data are sent at irregular intervals with the start and end of each packet being marked by specific signals involving such transmissions. I have no idea what that means. This might be interesting to you if you're at the level of designing packet-based, switching and low-level network protocol design. This probably makes sense to you. Most of us do not work in this context. Most of us work at higher levels of abstraction. So this definition is also no bueno. Software is a type of socio-technical system. This is a talk about meaning. We should explain what we mean by a socio-technical system. A socio-technical system is a system which involves people and technology. Technology defined more broadly than how we think about information technology. And before you think, oh God, this is going to be some kind of snowflake-based talk about some liberals saying, why can't we all get along? This is woke architecture, whatever. Actually, the concept of socio-technical systems actually came from studies into coal mining during World War II. But they were looking at how do we understand systems in which people and complicated technologies are working together? How do we make sure that those organizations and those systems are healthy and achieving the needs that we have for them? The amount of software created by an individual is vanishingly rare. The vast majority of all software we use is about people coming together. Linus, when he did the first initial version of the kernel, that was the last time he did anything by himself. The work he then put into was creating a community where tens of thousands of people could contribute to that code base together. Bringing people together to use technology requires that we can communicate with each other. We want to be in a situation where we have the same picture in our head. We're going to make this asynchronous. But if we have different views about what we're going to do, this is going to end badly. We're not going to be able to coordinate. And this is not a new idea. The importance of being able to communicate clearly and understand one another and what happens if this isn't the case is well known. This is the Tower of Babel. It's quite a famous painting. It's a painting inspired by a story in the Old Testament. It's actually a very short story. It talks about how the people of Babylon were creating a very, very tall, grand structure. It actually goes on, there's a bit in the passage, which is, as I said, very short, talking about how part of this is due to them having good technology. They've probably developed some sort of new concrete. But one of the main thrusts of this parable is this idea that they all spoke of one language. Now, some of you might be aware, the Old Testament God was quite different to the New Testament God. It was like a real kind of mid-season turnaround in character arc, right? Suddenly a different team of writers came in and had a different view of the world, right? The Old Testament God was a bit capricious, and in this situation, it's not really ever made clear in the parable itself. God looks down and thought, don't like that. And he didn't smite the tower, he didn't kick it over, he just stopped them all speaking the same language. That's all they needed to do. The Old Testament God said, you now have different languages. And that's how the tower was not built. The term asynchronous, even if we look just in the context of inter-process communication, had so many meanings that it is effectively meaningless. I was going to show you what was in the distributed systems book in Tannenbaum. So I searched the latest edition, the third edition, freely available, which you do with Van Steen. I think the word asynchronous gets mentioned 4 times in what is basically an 800-page book. Like, the authors of the distributed systems book are like, we are not touching that word with a barge pole for good reason. So what can we do? Understand what your application needs. Describe how you want your application or your system to handle different situations. What is important to the users of your application? What do you expect should happen when a server is unreachable? How fast do you need your application to be? What are you going to do if a client crashes? And where possible, use more explicit terms and take the time to define those more explicit terms. And we have more explicit terms. We have terms like request response. We have terms like event-driven. We can say things like the client should be non-blocking. We want operations to be run in parallel. We are going to use a broker as an intermediary. So when talking and communicating internally, make sure when you use these words, they mean the same thing to you. And if they don't, take the time to talk about them. But don't use words that are so widely used and have so many definitions, it's not helpful. Try not to make this about just correcting people and thinking you're smarter. Part of the joke in The Princess Bride is that, Vinicius has this version in his head of what it means. And we know as the viewers, all of us knows that he's using that word incorrectly. It's a bit of fun, right? But from the point of view of the conversations you have with your colleagues, they're not using the words wrong. They're just using the words differently. And it's not for you to say if your version of that word is better than their version of the word. So next time someone says to you, we should make this asynchronous, maybe all you need to say is, okay, what does that mean to you? Because what you find may shock you. Thank you very much.